A massive, heavy fish strike triggers a violent kinetic collision between human intent and raw, powerful aquatic muscle. When outfitting for this specific moment, we often fall into a gear specification trap. We assume that higher numbers on a spec sheet, specifically blistering reel speeds like an 8.1 or 9.1 ratio, make us unstoppable on the water. This diagram shows the mechanical definition of a gear ratio. It represents the exact number of times the internal spool rotates every time the external handle spins exactly one time. But an obsession with maximum rotations creates a hidden engineering vulnerability. Blindly prioritizing velocity brings the wrong physics to a heavyweight fight. At its core, a fishing reel is a rotational winch. A gear train built for high speed is engineered to move light payloads very fast, rather than deadlifting heavy mass. The system meets its limit the moment a 50-pound payload stops swimming, turns its head, and fully loads the line with kinetic tension. In this high-speed configuration, the data readout is slanted entirely towards speed. Lacking torque, the pinion gear cannot move a heavy, static weight. Under extreme pressure, it deflects off its axis, the teeth bind, and the entire rotational system seizes. This gear lockup is the mechanical consequence of exceeding the engineering limits of the materials under load. Every reel is governed by the conservation of energy. In rotational power transmission, the mechanical power delivered by the handle must equal the power received by the spool, minus friction. This creates a strict mechanical trade-off. In a closed system, generating extreme speed requires a direct sacrifice of pulling power. Generating immense torque requires a direct sacrifice of speed. High-speed reels are built for specific tasks. They allow for the rapid recovery of slackline or the manipulation of fast-moving topwater lures across the surface to trigger a strike. A low gear ratio system, like a 5.4:1, uses gears with larger, deeper teeth. These are engineered to transmit maximum rotational force with minimal physical effort from the angler. Selecting equipment requires looking past the highest number on a box and choosing the specific mathematical tool necessary to overcome the anticipated payload. We can observe the difference by applying that exact same heavy, static resistance against a low-speed gear train. When analyzing this model of a low-speed system, the UI readout prioritizes torque. Operating under pressure, the gears demonstrate mechanical stability and thermal efficiency. The calculated mechanical advantage of this winch geometry overpowers the kinetic resistance, lifting the heavy payload without warping the metal components. True stopping power is a result of optimizing mechanical advantage rather than maximizing rotational velocity. Tournament professionals routinely land massive fish on high-speed reels that mathematically lack the torque to handle them. They succeed by utilizing the missing half of the power transmission equation, the fishing rod. As this wireframe diagram shows, a fishing rod operates as a Class 3 lever. The angler's hands act as the fulcrum, applying the effort, while the rod tip acts as the load point where the tension sits. Because the effort is applied so close to the fulcrum, this lever operates at a mechanical disadvantage. However, it successfully transfers the physical strain away from the delicate reel gears and into the high-tensile composite blank of the rod. A high-speed reel is a specialized tool that depends entirely on being integrated with the lever to survive a heavy fight. Effective combat technique requires the angler to use the rod's leverage to physically move the fish, never relying on the reel's gears to do the heavy lifting. By pumping the rod back, the angler forces the composite blank to take 100% of the kinetic load, manually dragging the payload closer. Tracking the rod's flex, dropping the angle from 90 degrees down to 45 shortens the effective length of the lever. This increases direct force applied to the fish by up to 40% for the same physical effort. In the final phase of the maneuver, as the rod tip drops forward and tension momentarily releases, the high-speed gear train is engaged to blur into action and pick up the slackline, bypassing the torque penalty entirely. Mastering the catch requires combining the lever for raw power and the gears for pure speed.